Note that our equation for work related to P times dV integrated from V1 to V2. So basically, we've just said it's the area under the curve for our PV curve. So this is really helpful. Now, one thing to remember is that work had that minus sign in front of the integral. So what that means is if your final volume is actually bigger than your initial volume, such that you're integrating on the v-axis from left to right, you actually have to say this is negative times the area. So even though we would typically consider this a positive integral, there's a minus sign in our equation. On the other hand, if we have an initial volume that is larger than the final volume, we would consider this a negative integral. However, there's a minus sign on the equation. So what this means is that negative work is done on the gas here, and positive work is done on the gas here. So positive work, negative work. I actually find it helpful to think about this version first, that we've done positive work on the gas if the final volume is smaller. And effectively, imagine that you have the canister of gas in your hands and you are pushing on the piston. The piston goes into the gas. That's also the direction that you've pushed on. Clearly, work has been done. The gas volume has also gotten smaller. So your final volume is smaller because you've pushed in, right? Again, we're talking about work done on the gas. So you've pushed the piston in, the volume got smaller. That's positive work. Does that make sense? I think that that is the easiest way to think about it because the expanding gas is then the opposite. Your final volume is larger than your initial volume, and that is the environment doing negative work. And I think that that's a little harder to understand. So again, I would say if you can just think through something, think through this case, which is that final volume is smaller corresponds to positive work. And this is always going to be the case since we can't ever have negative pressures. So keep in mind that we don't have to worry about any other reason for our sign on the integral to actually switch. We have a new problem-solving strategy. First, some modeling. We always now need to model the gas as ideal, and we need to model the process as quasi-static. It's really helpful to visualize this using a PV diagram. You may also want to use some bar charts that we'll be introducing if you find that helpful, but the PV diagram is really essential. You want to label as much as possible, including if it's one of the special processes, including adiabatic. Now, what we're usually going to need to do is calculate the work done by integrating the PV curve either geometrically or by carrying out the integration. Frequently, you can actually do this geometrically, and there are going to be cases where you're given a process that is not one of the special ones, but does actually facilitate a simple geometric integration. Remember that this is the equation that it has a minus sign here, and that pressure might be changing depending on what type of process it is. Check your signs, and again, make sure that you remember that positive work is when the gas is being compressed, and that means that energy has been transferred from the environment to the gas. If the volume hasn't changed, no work has been done. So that's the general process. We will be building on this by adding heat very soon. Now let's go through the special processes and look at their PV diagrams and think about work. So isochoric, the volume is the same. Again, that means a vertical line on a PV diagram, and if you say what's the integral here, well, it's 0. Negative of 0 is still 0. So no work is done in an isochoric process. In an isobaric process, we do have a constant pressure, which means in that integral you can actually pull out pressure, and then you just get to multiply pressure by the change in volume. Neat. But remember your sign. If you have an increase in velocity, in volume, that delta V is positive, you have negative work done. Remember that delta V is equal to V final minus V initial. So make sure that you get your signs right. Frequently, we're not going to be involving zero volume here, since that doesn't make any sense for an ideal gas process. So make sure that you're getting your subtraction right and actually getting your sign right here. So that's really important. But for an isobaric process, you don't actually need to do any integration. You can just multiply. Isothermal processes, we still get to do an integral, but note that now both your pressure and your volume is changing. So if we start with our form, again, negative integral of PdV, we note that we can use the ideal gas law to express pressure in terms of other variables. In particular, we can express it in terms of temperature, which is constant, and volume. So we literally sub in P equals nRT over V. So PV equals nRT, rearrange for pressure. So now we have some constants and V, which is what we're doing our integral over. Note that we haven't lost our minus sign. So when we do the integral by pulling out the constants, we now have dV over V, which you should recognize as a natural log. The book goes through a few other steps in between and how you can actually rearrange this, but note that you then can actually write this as the natural log over V2 of V2 over V1. Your nRT hangs out in front, and then you still have your minus sign. So this integral is actually a little more complicated, and we're going to get to an even more complicated one with the adiabatic one. So please make sure that you're remembering to actually do the integral here and not just treating pressure as constant. And again, identifying what type of process you're working with is a really important step. Now, I'm not going to go into the adiabatic process since we have to talk a lot more about that before we easily define the work, so I'm going to leave that for a later video. However, I do want to highlight that work depends on the path. So I can have two states that are connected by two different processes. Note that the integral under these curves are different. So I can have one method of taking the gas from state I to state F that does this amount of work, remembering that that would actually be the negative area under the curve, that is the work. But then I can use a different process to take it from state I to state F that actually does a different amount of work, shown here in the turquoise color. So please be careful and remember that you can't just use initial and final state without the process information. You must use the process information to actually figure out what the work is. So in this case, the magnitude of the work of process A is larger because there's a bigger integral under the curve, but keep in mind that it's the negative integral, and if you look, you're going from a smaller volume to a higher volume. So in both of these cases, negative work is actually done. We can then look at a picture like this, where we actually have multi-steps, and note that in one option, we've taken state 1 directly to state 3, and in another case, we've gone through state 2, then to state 3. Note that in this case, going from 1 to 2, because this would be a positive integral, that actually means you have negative work. So we have negative work done going from 1 to 2. But then from 2 to 3, we would have a negative integral, which means you have positive work done. And note that obviously the integral, the magnitude of it from 2 to 3 is much larger than the magnitude of 1 to 2. But if you look at the process taking the state directly from 1 to 3, there was no work done there because that's an isochoric process. So this is something that's really interesting, that I can transform my gas in one way that has no work done on it whatsoever, but I can transform my gas in a different way through two steps that have opposite signs of work but not equal magnitudes. And what that hopefully shows you is that if the final state if I've gotten there in two different ways, this state has to have a specific temperature. This initial state has a specific temperature, but the work done is different. Clearly something else is changing my thermal energy. We've already introduced the idea of heat, and that's going to come in here. So we can also relate these PV diagrams and the work done to heat, as we will be coming to very soon.